Good morning. We're live coding today and the topic is JIT flushes in RaptorJIT. Now, a JIT flush is something that happens when the JIT has generated a bunch of code and for some reason or another it decides it wants to discard all of the code that it's created and re-record from scratch. The basic idea behind doing a JIT flush is when your workload might have changed significantly. If you've changed your configuration or something like that, it might be a time when the code you've generated is not optimal for your new circumstances, and it's a good idea to discard the code and record it again. JIT flushes are pretty cheap in principle. So the JIT runs very after you do a JIT flush, you don't have any machine code anymore, so your program is going to run interpreted. Certain parts of the program are quickly going to get hot and get recompiled, and really actually quite quickly you'll be back in the situation of running everything in JIT mode again. So it's in principle a pretty cheap operation, but it has a few significant complications that we need to think about today. I'm going to pull up a list of these. Right here. So, the first thing we need to fix is a problem that can cause thrashing that was reported, and I think I've tracked down. Just give me 1 second. The boys have some needs this morning. Yeah, a thrashing bug. So I think this is a bug that I've introduced in RaptorJIT that wasn't there in LuaJIT, which is that when you have a lot of traces, you can get into a situation where it starts thrashing, it starts flushing in a loop. I think I see how this happens, and I think I know what to fix is. So we're going to reproduce that and test it. Then, when we flush the JIT, we need to tell the profiler we've done a flush. So the profiler in the VM is always kind of keeping track of what is the most recent trace of machine code that we executed, and it uses this to attribute profiling samples to say where they come from. So when the profiler wakes up and says, what am I doing? It looks at what trace to blame, and that could go stale when we do a JIT flush. So when we do a flush, we want to clear out any state like that so that we don't attribute work to a previous generation that actually doesn't exist anymore. We also want to log every JIT flush into the audit log. Now, the audit log is the log file that the JIT generates to show all of the activity that it's doing when it creates traces, when it compiles things, and so on. We need to log flushes there. We don't do that today, so we don't have any visibility into flushes after the fact, which is problematic. Then a bit more advanced, if we get this far, we need to extend the VM profile file format for our profiler data to be able to span multiple generations. So I would really like, a JIT flush could happen any number of times. You might do it 1,000,000 times, but it would be nice to have the last, n, say 5 or 10 generations profiled. So when you were running an application, if you would do a flush, that you would get like a profiler data set for the pre-flush code and then a separate one for the post-flush, and then you could compare them. And then we would need to extend the user interface to make those comparisons. So this is a pretty big agenda for handling JIT flushes in a good way in RaptorJIT and Studio. We won't get through all of this today, but let's just get started and see how far we get. So we're going to dive into this max traces thrashing bug. So the thing here is somebody Raj in Snabland reported a problem where his application would reach a state where it just starts spinning around, flushing all the time. And I think the reason is that the VM thinks that it's got a lot of traces, that it's got too many traces, and it's doing a flush to try and get that back down to 0, but the flush is not working. And the reason is some code I'm going to pull up. My theory, at least, is that when we look in here, we'll see... We'll see a utility function for getting a free trace number. So the basic operation of traces is the JIT operates by the virtual machine operates by interpreting bytecodes, and then when it notices that it's running the same bytecodes a lot, then it wakes up the JIT, and the JIT generates a fragment of machine code that represents just one specific sequence of bytecodes, and then it generates a bunch of these so-called traces and patches them together, and that's how the program ends up running mostly in machine code. And every time it wants to make a trace, like a fragment of machine code, it needs to give it a number. They're always just numbered, and the numbers go from 1 up to 64k. So it seems like you've got a lot of those numbers, but there is also an option called max trace, which defaults to 1000, which is the maximum number of traces that you want to have. So this is a parameter of the JIT that says if we've got this many traces, then maybe that's too many. Maybe we should, if we reach that point, maybe it's a good sign that we should start over, because the working set shouldn't be that big. And I think we've got a couple of problems here. One is that number might be a bit conservative. So some applications actually will generate 1000 traces, and there's nothing wrong with that. So that number is probably a bit too low. But the other thing is that I think when the code, the way the thrashing happens, I think, is the code comes in to find a free trace number, and if it gets a number that is beyond, it doesn't want to use a number that's above the maximum trace limit. So this is how the max tracing rule is implemented. It puts like a ceiling on the trace number that you can get. So if the trace number is going to be above the limit, then it's not going to give you that ID. It's instead going to return 0, and that's going to cause a flush to say that, hey, we've gone over our limit. And in LuaJIT, this works fine, because in LuaJIT, every time you do a flush, the trace number rolls back to 1. So the IDs are reused every time. But in RaptorJIT, I'm not doing that actually. So in RaptorJIT, I changed it so that the IDs don't get reused after a flush. So if you generate 100 traces, or in this case 1000 traces, and you hit the limit, then you do a flush, and then you don't have any traces anymore. And in LuaJIT, the next trace will be called number 1. So you have another trace with ID 1. It's been recycled from the trace we had before the flush. But in RaptorJIT, you get the number 1001. And if you flush again, these numbers don't go down until they cross the threshold, which is 4K. And the reason that I'm doing that in RaptorJIT is that I want the profiler to be able to span across. I want the profiler to be able to span across flushes. So it's going to be very confusing if you get a profiler sample that says it's talking about trace number 1, for example, but you've had several different traces that all had number 1. Also, rather, when you load up the profiler dataset, and it says, well, we recorded 1000 samples for trace number 1. Well, if you have 5 different traces that have all been number 1, you don't really know which one it's talking about, and they might represent completely different code, because the numbers don't kind of map to the source code in any specific way. So somehow this is not quite satisfactory, and we need, for this max trace parameter, we might want to even increase the default. Might even just pencil that in right now. Instead of being 1000, we might make it, say, 10,000. And then we want to make sure, we want to actually enforce this in the correct way. So when we go into this function we had over here, we were looking for a free trace number. This is supposed to return 0 if we're over the limit, but the limit should specifically be about whether we have the limit should be about whether we have too many traces that are actually active, not on the trace number, because in RaptorJIT the trace number keeps going up, and once it crosses this limit, then it's going to always look like the table is full, even if you have no traces, and that's the problem. So the question then is how we want to implement this. So when we look at the max trace, we're going to limit on the maximum number of traces that we're willing to have. And then we get the number of traces that we have is this size trace. Okay. So that's the problem, is that this size trace goes up and doesn't come down again. So actually maybe we just gotta make let's see what the definition of this size trace variable is, and then see if it already has the right meaning, and if so, whether we need to maintain it a little bit more carefully. Let's have a look. So if we take jit.h, size of trace array, a little ambiguous. See how it's used. Okay. So this seems to be in conflict. So we have an array of traces, and this grows dynamically. Gets allocated small and it grows over time. That's what these allocation routines do. But when it reaches a certain size, we say that's too many. And the thing here is, let's think about this a little bit. So yeah, right. So the trace ID is an index into that array. If we want to have larger trace IDs, then that array needs to be bigger. So the size, as we have things now, the size of that array is not going to correspond directly with the number of active traces, because we're leaving the bottom slots after we do a flush, we just kind of leave the bottom slots empty. And I feel like we've got two things that we could do here. One is that we could continue on the path we're on of not reusing trace numbers, so that when you do a flush, then the new traces will get new numbers, and you could share multiple generations in the same profiler dataset. But as I think this through and talk out loud, I don't like that idea so much. I think maybe it was the wrong idea to begin with. I think maybe it's better if we do reuse the numbers. So when you do a flush, the number does reset down to 1, but that every time we kind of reference a trace, we keep track of what generation that belongs to. So if we have trace number 1 for the first generation, this could be trace 0.1, generation 0, 1.1, generation 1, trace number 1, and then if you do a flush, then you would get 2.1, which would be generation 2, trace number 1. And then the profiler would need to take this into account with the profiler datasets. We would need to always say in a profiler dataset which generations does this correspond to, and there would always have to be just one generation per dataset. So what we would lose is the ability to mix multiple generations of JIT code, across flushes in the same dataset, because the numbers, the trace IDs would not be unique. But that might be okay, because I don't think we particularly actually want to mix multiple generations into the same profiler dataset. Actually, I think every time you do a flush, I think on a high level view, so we pull up the Studio UI for a moment, we would run a set of benchmarks, we pop up and we get profiler data here, and we can click through and see from the profiler dataset down to a source code location, and then we can see the code that ran there, had that look, and all the rest of it. Now, the way that I'd like to browse more complex datasets here, if there were JIT flushes, I think what I would like to do actually is see some tabs here, where I would look at each generation separately, because when you flush the JIT, basically you're saying, now I want to start over with the machine code. You know, now I think that my workload has changed in some significant way, and the generated code, you know, maybe you've made major changes to your configuration or something like that. So then you want to just start over in terms of machine code. And then I don't know if you really want to mix everything together in the profiler. I think it could be quite nice to look at the generations separately. And so in that sense, if we're going to look at them separately, then we can reuse the trace numbers, because we're not going to mix them up. We're going to have this kind of separation. So I think we might go that way, you know. I think we're going to try to take that and run with it. What we're going to do is, first, in that case, we're going to roll back the change that we made to stop reusing trace numbers. So we are going to reuse them. And then, if we pull up our to-do list again for a moment, we already have a bunch of, like down here, we want to make the profiler understand multiple generations. So we're just going to have to do that in a kind of a sensible way. So yeah, if we're going to solve that problem anyway, of clearly and properly supporting multiple flushed, you know, generations of machine code in the same profiler dataset files, then it's okay. Then we don't need to make the trace numbers unique. So we're going to fix this bug by reverting to the same behavior that LuaJIT has, that after a JIT flush, you'll keep on, after a JIT flush, you will keep on, you'll go back to trace number 1. You reuse all of the trace numbers. And we're going to need a test case to be able to make sense of this, so let's write one. The problem we have now, I think, is if we have code that has at least 1,000 traces, then that's going to cause kind of endless flushing, and we want to fix that. So if we write a program now that will have more than 1,000 traces, how do we do that? Well, we could write a loop make it short for now. It's a nice case to illustrate, actually. So what I want to do here is I want each of these iterations, 1,100 of them, to each form a different trace. So how do we do that? So if we think about how the JIT works, it's gonna, if we would just run this code, we'd come in, it would see a loop, we'd enter the loop, we'd come in here, see another loop, it would get to the end, and it would branch back, and it would come down here, and it would branch back, cut out here and branch back. And after about 30 steps through that, it's going to say, okay, this is hot now. And say this inner loop, we've run it enough times that it's time to wake up and compile that. And so then we'll get a root trace starting on this line. We'll then run in here. And then, so that would be one trace, just as it is here. And then what would probably happen after that is that trace would finish, it would return to the interpreter, I would imagine, and it would come up here, and it would go in here, and it would see that that's already compiled, it would run the JIT code, and go around again, and then after it gets up here for the 30th time, then it would decide that this is also worth compiling, and it would compile a little bit of code from here that would just run to here, and connect up with the trace that we have there. So we would probably end up with 2 traces, I would imagine. I'm not sure if we would actually get anything compiled from the end here looping around. And 2 traces are not enough, right? We want a lot. So we want to put something in here that is going to cause a different trace to run for each one of these. So when do you get a new trace? So what would cause this loop to branch out and make a separate trace. And there are two things, basically, actually, that cause you to make a so-called side trace. One is different flow of control. So if we had an if then else here with 1100 branches, that would be one way to do it, but that would be a little bit inconvenient because usually there's only so many paths of control, really. I guess that we could do something. I guess we could do something nested there, actually, in terms of control if we wanted to. It might be reasonable. It might be something that gives us a satisfying little kind of combinatorial explosion. But I think an easier way is, one way to get a side trace is to change the control flow. The other is to change the type of some intermediate variable. So if we can just access 1100 different types of objects here, that would do the job. And that's actually pretty easy because we have an easy way to manufacture new types, which is with the FFI. Every time you define like a C struct, that will become a new type as far as the JIT is concerned, and it would need to be compiled separately. So if we would actually just say, suppose we've got a table of types, and we say that if types J is nil, if we haven't defined type with that number yet, then types J is a struct. That should assign, we could really do that just out here, couldn't we really? We could just say that. Get an empty table, we fill it with a lot of types. I'm going to need to load the FFI. And then we could just basically do anything with that, right? So if we load that object into a local variable, the JIT, when it generates the code, is gonna put a static type for this machine code on that local variable, and the type will correspond with the exact type FFI type object we have in this array. So all we need to do is load the value into a variable. And in such a way that that it won't be optimized out, which we might need to think about. We need to do something with it. What about if we would say values? We're just gonna copy it. I think we will say values. That should be J. So the gambit here is that by loading a type here and saving it there, this should be stored in a register at some point, and the JIT statically types the registers. It does. That's just how it works. And on the first loop through, it's going to get the static type of the first struct that we created, and on the second one, it's going to get the second type, and so on. So we should get 1100 side traces there. And actually, this is pathological code, so this might actually be a problem. I don't know if this is going to blow up the VM or... Oh crap! There's a limit on the number of side traces you can have, isn't there? Okay, so maybe this is a little bit too aggressive to try and do everything in the same root trace. So we might need to get several of those. The easiest way to do that, might just be with a copy and paste a little bit, not too much. What's the normal maximum number of side traces that we get? 100. Okay, so ordinarily you get at most 100 side traces. So let's just have 100 types. And let's just have 11 of those loops. So now it's a bit different. Now this will be a root trace, and it's going to have 100 side traces. This will be a root trace with 100 side traces, and this will be a root trace with 100 side traces. So when you add all of that up, you should get quite a lot of, you should get over 1,000 traces. And now that I think about it, we could make it a bit simpler as well, because that max traces is configurable. So we can also say jit.op.start max trace equals 100. That might make it a bit easier, might it not? Let's say max traces equals 50. That makes it a bit easier, doesn't it? So then already the first time around, just creating 100 traces, we're going to go over the limit. That's looking better. That shouldn't blow anything up. That should be a nice little test case. Let's see what happens if we run this. Well, let's make it iterate a little more. Now, I'm just going to very crudely see what it's up to. Is it doing a lot of JIT flushes or not? It's not particularly doing a lot of flushes actually. But these, I believe that these correspond with JIT code, so it doesn't look like it's running flushes all the time, which is what I had expected that it would do. I'm going to try running that. Actually, use LuaJIT just to see what it says is the activity. Okay, so I'm wrong. It's not. So this is nothing to worry about. That's this loop up here. Down the bottom. Okay. Somehow this is not actually giving us not actually giving us side traces all the time. Why not? Are we getting new type objects there? Yes, so we are getting new C types all the time. So maybe it's just that the compiler was smart enough to avoid specializing on the type here. I'm actually going to read the intermediate code to see. Okay. Yeah, it doesn't seem to be specializing on the type. So let's make it do that. Let's give these structs all a value x, and let's load that x. So now we're actually accessing some C FFI data. It should presumably then have to specialize. Oops. I know, but it's a type. I mean, it should be an object of that type, right? Not. That's my mistake. So as I said, the JIT statically types the value of every local variable, but it's saying that the type is a C data type, because that's what I'm giving it a C data type. I want to give it an instance of a C data type, and then for those instances to all be of different types. So let's change that to be FFI new, and now see what happens. Okay, it's still not. So now how does the code look? Looks the same. What have I got wrong there? Okay, let's do this trick again then. Oh, sorry, let's see. Okay, but that's more like it, right? So now we are indeed getting a lot of traces. Hold on, so take out these printouts that we don't need. And, okay, now that's running with LuaJIT, and that's looking like what we want, actually. We get to the 50th trace. Neat. Okay, hold on, let's scroll up and just go through this. That's pretty interesting. It's a flush, and then it kind of looks like it's thrashing. But we're running LuaJIT there. I didn't think that LuaJIT would thrash there, actually. I thought that this was going to be a RaptorJIT specific bug. Maybe it's for both. Let's Let's have a look. So this is when we're generating the types, that doesn't matter. Then we get the first real trace. And then we get a bunch of side traces in there. One for each type that we defined. And when we get, after we've recorded the 50th trace, that was our limit that we set, then we get a flush. And we start again counting from 1. Oh yeah, that makes sense. Okay, no, this particular brand of thrashing does make sense, because the problem that we have here is we set the limit so low on 50 that our actual working set of traces is bigger, so that we just set the limit too low. So now we're testing with LuaJIT, and this is not a bug, this is just the expected behavior. If we set the limit on the maximum number of active traces to be smaller than what we need to actually compile our working set, then we're going to get these frequent flushes. So if we run this with RaptorJIT, I'm expecting to see something similar, but not quite the same. And it's a little bit tricky to see with RaptorJIT because we don't have this command line tracing. We only have the logging into the audit log, and the audit log currently does not support tracking traces. So that's something that we're going to add today, we hope, very soon. So to see the same information with RaptorJIT, we need to dump the log, but the log doesn't contain what we need at the moment. Anyway, I think if we run this with RaptorJIT, we're still going to be able to see what's going on. It's spending a quarter of its time doing flushes. So I think it's a tighter thrashing loop here, because I think what happens is, this is just going to be a really basic comparison. I'm going to run LuaJIT again and just compare it there. And I think it's going to spend less time flushing because it's not thrashing as tightly. Is it running? Oh, sorry, I had pipes there. Sorry, now it's running properly. So where is the process? Is it running? Yes, it is running. Okay. Interesting. So is that actually not CPU bound? No, it is. We saw it there, running at like 100%. The perf is also running 100%. Okay, I don't know why perf is so overloaded. Anyway, when we run the LuaJIT one, I think what's happening is it's spending all of its time compiling things. I think that's what happens on the LuaJIT side. It generates 50 traces, throws them away, generates them again, throws them away, generates them again, throws them away. But I think that what is happening on the RaptorJIT side is tighter than that. Again, we run with RaptorJIT, and we run the profiler here, and we see it's actually spending a tremendous amount of its time actually doing the flushes. And I think the reason for that is that once the trace number goes over 50, then it flushes, and then it immediately flushes and flushes and flushes and flushes and flushes again. So it's not actually compiling any code, it's just kind of wedged in a state where it thinks that it's always kind of got too many traces and needs to flush, but the flush doesn't help. So anyway, I think if we back out our change that prevents the trace numbers from being reused, we should see the profile here go back and resemble the other one a little bit more. So I don't know immediately a better way to test this, because this is not like a correctness thing, right? In both cases, the program is running as kind of as expected, but just one moment. Yeah, so in both cases, the program is running, the JIT is active, and it's doing a lot of flushes. It's just in one case it's doing a lot more flushes than in the other, I think. And I think a reasonable way to observe that is with the profiler. So we saw the RaptorJIT process is doing way more time flushing, because I think that's almost all that it's doing. So we'll pull out the code, and we're going to find the file to begin with. Free trace. I think, if I recall correctly, LuaJIT moves this free trace back to 0 or 1 after a flush, and RaptorJIT does not. I think that's what it was. So we're going to do a git pickaxe search for changes that modified a line involving free trace. We're going to say git. Isn't that the pickaxe syntax? There's the commit. 2 commits. So, make trace numbers unique, stop reusing them. Make JIT trace numbers unique for completed traces. This way a trace number is an unambiguous way to refer to a GC trace object even across the flushes of the JIT. The immediate motivation is to make the VM profile data valid across JIT flushes. It's counting the samples by trace number, so that when trace numbers are reused, the multiple traces can collide on the same profile counter. And then this is perhaps a follow-on kind of fix-up. So we look at that one first. So what did we back out? When you do flush all, it was resetting free trace to 0. And it was quite eager about reusing things actually there. Oh, I don't know if I like that. That one seems to be saying that if you would flush a single trace instead of all traces, that you could reuse that trace number, and that I don't like, because again, for the profiler, we're going to say that we have a generation of machine code, which is everything up until a flush happens, then it's the next generation, so the next flush, and the next generation. Then we would still want the trace numbers to be unique within a generation, because then they get a profiler bucket. So you wouldn't want to reuse some particular trace numbers within a generation, because then you won't know how to interpret the profiler data. So I don't think we want to back that out. What about this? Find free. Not immediately sure what the reason for that is, but let's look at the other commit and see if that sheds any light. This was the other commit. Okay, these maybe came from different files because those are both doing the same thing. Okay, so this change here is redundant because it's already included there. So there's only one commit that we actually care about, which is the first one. And another look at that. Starting from the bottom, going up. Now we want to revive that line of code. After we do a flush all, we do want to go back and consider all the trace numbers to be available. So we're going to put that change back. We're not going to put this change back because this is this is a more fine-grained kind of a thing, where if we're just kind of freeing up one trace, if we put this back, we would be kind of like very eagerly trying to reuse trace numbers as soon as possible. And it is possible that an individual trace is flushed rather than a whole generation. So in the cases where that happens, we don't want to reuse the trace number. So we're going to leave those lines out. We're going to revive that line. We're not going to revive those lines. What about this line? Find free. At the end of find free, do we increment free trace or not. So we were not incrementing it before, and now we are incrementing it. Why do we need to do that? Let's read the code and see. This is this function here, and it's this line here. So we added the increment on the free trace. Did we really need to though? We're looking for a free trace number. If we don't know which traces are free, we start searching from number 1, because they do start counting from 1. There is no trace 0. Then we loop up to the limit of the trace array size, and the trace array then is being dynamically allocated. And generally in RaptorJIT we've been taking away a lot of these dynamic allocations because it just seems a bit gratuitous. You know, if we only need 100 kilobytes of memory or something, I tend to prefer to just allocate it up front and not bother with the complexity of dynamically reallocating it and growing it. But anyway, we don't worry about that right now. We scan looking for a trace that is free, a slot that is free, and if we find it, then we return that, and we know that that was the first. It's this code is actually a little bit clever for my taste in the sense that it's maybe it's okay. Maybe it's okay. Just wondering if it's really necessary to update that, because it seems like we should be able to search pretty quickly through this. But anyway, let's not worry about that right now. It's possible that this could be made a little bit more silly, and it's possible that would be a good thing. It's also possible that would be a bad thing. So let's not do that right now. If we find a trace slot that is not in use, then we return that value, that slot, and we increment the free trace number so that the next time around the search will start from that point. So we kind of cache the memory that there are no available trace slots before that. And if we didn't find an already free slot and we get down to here, that means we're going to try to expand the size of the array. And we say the limit is our max trace parameter, with a lower clamped to a lower bound of 2 and upper bound of 64K. And then we look at how much space we already have, and if that is already on the limit or above, then we can't grow the array. So we have too many traces, so we have to that's going to cause a flush. We return 0 here. We say, I'm sorry, we can't find a free trace ID, and that's going to cause a flush. Otherwise, we grow the array and we fill the new entries with nulls, and then we return this number. So returning that number of what is now the latest. Hold on. Okay, so the free trace has been getting incremented all the time here. So by the time we get down here, the free trace is pointing just beyond the end of the trace. I don't know. I feel like this function could be a little bit simpler. So this search for free trace has the side effect of advancing, if it fails to find a new one, has the side effects of advancing the free trace number to, oops, what was I doing? has the side effect of advancing this free trace number to be just after the end of the array, and then it's out of bounds. Then we come down and we grow the array, and so the trace number is this is going to be the right number for the trace, and then it kind of makes sense to post increment that, because now we've returned this number, so that number has been used. And so if we do that increment there, it's the same as doing this increment here. So I think you don't need the increment there and you don't need the increment there, but they have the same function. It just means that the next time we come in looking for a trace number, we're going to start looking at the number after this. So what about when you get aborts and that kind of thing? You know, what about when if we get this number and then we try to make a trace and it doesn't work? Maybe that's the idea here. So I think we're going to put that back, because we got no actual specific need for bumping it there. It's just a nice to have. It's possible that will actually skip over trace numbers, I think. Possible. Okay, so hold on. If we take these thoughts back in here, we had 3 changes in the diff that we were thinking about reverting. What we're saying is we are going to revert that, because it doesn't look like there's a strong motivation for having it. It might actually be a little bit nonsensical. Well, it might be a little bit of a waste of trace numbers. It could potentially assign a trace number that is not used and then not reuse it for the next attempt, which would be a pity. I'm not sure, but anyway. Seems like the conservative thing is to roll back that change. I do not want to roll back that change, because if we free one specific trace, I don't want to reuse that trace number within a generation. I only want to reuse trace numbers after we do a flush. That brings us down here, where when we do a flush all, we go back to the start, consider everything to be fair game. And I want to have one more look at the other commit. Oops, that's the same one. Is that actually the same change? The line above unpatched blacklisted bytecodes. No, was it another case? Hold on. Let's look in flush all. So, okay, so that this was some code that was added. So the reason we saw the same change twice is just that it was in a bit of code that has been changed. So it was only one logical change. So this so what we actually want to do is we're actually going to do it as we say it now. If we pull up the first diff, we want to roll back this change, because when we assign a trace ID, we want to keep assigning that ID until it's actually used successfully. So if we give an ID and it's used for a trace attempt and the trace attempt fails, we want to use that ID again the next time. So then it's better to leave it like this. In the code, that's what we already have. Good. Now on the next change, we don't want to bring this back, because that would eagerly reuse a trace number within a generation. So that code is gone. We don't want to bring it back, so no action is required. And here we want to bring this back. We want to set free trace to 0 in flush all. At the same time, we pull back the trace number there. Here we want to say that, if I'm not mistaken. And that's all. That's actually all we want to do. And the effect of those changes should be that when you do a complete JIT flush, you'll start counting from 1 again on your trace numbers. And that would be confusing if you were going to use the same profiler data set for multiple generations. And that was the thinking behind behind kind of trying to make the trace IDs unique before, but now since we're going to add some smarts to the profiler to be able to track each generation separately, then it's going to be okay to reuse these numbers, because we will, on the profiler level, we will arrange it such that when we say trace number 1, it is clear whether we mean which generation of JIT code we're referring to. And the simplest way to test that now would be to run our test program again, and if we go into the profiler, is it going to look more like before? No, it's still in the flush, or even more so. But that's a surprise to me. I was expecting that to go down. We might need to let's have a sanity check of the code, and it's possible that we will need to come up with a better way to test this. But now let's just see. Okay, so it's still running in the trace hole. We did not see that behavior with LuaJIT, right? I don't know why perf gets so overloaded when we're out with LuaJIT. That doesn't make any sense to me. A little bit useless. So, since I don't think that test case is particularly good. I don't know why perf is misbehaving, but since one of the next things on our to-do list anyway is to log flushes in the audit log, maybe we'll test it in that context. So we'll put the flushes in, and then we'll be able to see whether this fixes the kind of the thrashing problem. And the way that we would see that is we're thrashing if we just keep going flush, 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 whereas we're kind of not thrashing in a bad way anyway if we re-record all the traces and then flush when we hit the limit, and re-record all the traces and flush when we hit the limit. That would be the expected and desired behavior. So I'm going to mark this one, minus for not done, plus would be for done. I'm going to use a slash to mean we have to revisit it. We've written the code, but we haven't really tested it properly, and we're going to have to come back as our work progresses. So now we're going to do the next bit, which should be pretty straightforward. Well, hold on, let's commit this first, shall we? We'll do the 2 commits, and we'll create a branch. Which branch are we on now? The audit log branch. Probably fine. We'll just commit it there. This is a kind of an active development branch. That's okay. So we will and we'll get this. No. Fine, that is committed. So, we have tentatively made the JIT happy to reuse trace numbers after a flush. So you generate a bunch of machine code, you run jit.flush, and then it starts recording machine code again, and the trace number can start from 1. So you can keep on spinning through the same numbers over and over and over again. That's going to confuse the profiler because you're going to have multiple traces with the same ID that are all going to be counting into the same profiler buckets. But we're going to get to that. We're going to extend the profiler to have more buckets, but one step at a time. The next thing on our list is to clear the last profiler state on a flush. So this is kind of a semi-related thing. When we do a JIT flush, we should update the VM state to so the profiler will know that we're not running any of the old code anymore. So after we do a full flush, we should just clean out a little bit the state. So if we look in LJJIT again, there in this great big JIT state struct, which represents the basic state of the JIT compiler, there is going to be a little bit of state that relates to profiling. Where is it? Or somewhere hereabouts. Maybe it's in the global state, actually. Hold on. A global state object. It is at least and possibly only this field here, the last trace. So when some machine code exits back to the interpreter, it remembers where it came from, what was the most recently executed machine code, and that's so that the profiler can then blame that machine code for us running in the interpreter. But if you do a flush, then that's not kind of valid anymore. So this should get reset when we flush the JIT, because it's referring to code that doesn't exist anymore. You can't blame flushed traces for the reason you're in the interpreter. And the reason I'm focusing on this is that I got a data set that was a little bit confusing. It seemed to be blaming one trace for a lot of stuff that didn't obviously seem to be its fault, and I think it was just this value being stale. So when we do flush all, and we clear those, we're also going to get our hands on the global state somehow. Remind me, how do we get from the Lua state to the global state? G, okay. So we are going to want to say global state G is that. And then when we do those, we're also going to want to say that G, what do we call it? Last trace is 0, which means no trace at all. We'll run the test suite, shall we? Should probably have done already the last change. We build with Nix. The default behavior is to run the test suite at a bunch of different optimization levels. It runs really quickly, so there's no point not doing it kind of on every commit. Optimization level 1, pass 2, 3, get disabled. Okay, fine. We will now commit that. But it's just a minor fix. It's nice. Log flushes in the audit log. This will be nice. So, and it should be relatively easy. So we have our little C module for logging events to the so-called audit log. And, oh, we already have LJ audit log trace flush. Have it declared there. So we basically just want to make sure this function exists and that it's called. So it's declared. So is it actually implemented? No, okay. So we'll implement it. Now, maybe we'll call it flush all, because we might at some point want to track flushes of individual traces. We won't do that right now, but it's probably something that we are going to want. So we're going to want to log an event called flush all. We call the other event trace flush all. And it would be nice to put a kind of a generation number in here. We don't have that concept at the moment, but I think we might just log the whole JIT state object, and then if there's any state that's relevant in any way, we can just find it in there. So, you know, the way that this log works is to be pretty generous with what it records. So it's going to pick some C structs out of memory and write them onto disk. Any object that seems particularly interesting. And in our case, I think the kind of the global JIT state is something that we're going to want to log. So then if there's any kind of context that's significant, we can find it in there. So JIT state, did already say that. We are going to log the JIT state, and we're going to log the flush all, which is going to have one parameter. In the future, we might want to extend this as well and say why the flush happened, because it can happen explicitly on request. It can also happen heuristically. It would be nice to record that, but I don't think we need it right now. So we're going to log the JIT state, the raw out of memory, and then we're going to log an event, which is a trace flush all. It's going to have one parameter, and that's going to be key value. The key is going to be the string JIT state. It's going to be exactly the same as we have up here. So this line is going to actually pluck the JIT state object out of memory and write it as a raw binary image tagged with this address onto the log file. And then this is going to say that it's now a high-level logical event of a trace flush all. And then this line is going to say that we have a kind of a parameter of that event called JIT state, and the value is going to be the address that has in memory. So then we can go and find the object that was logged based on this address here, which will be very nice. And then we've got to make sure this is called as well. So in this function with the flush all, that should perhaps. Well, this is interesting. We need to pick the right place to call this, because we're going to log the JIT state object, and we're messing with that as we go. I think we want to do the logging actually very early, before we have a chance, before we do all of this resetting. So all the way back here, we want to say that, I would say, and we'll see if we can build and run the test suite. Yes, we can. All of the tests passed. And now we could test that a little bit actually. So if we would run a little, let's make it another tiny little program. It's going to say it'll do something that generates a trace, and we'll call jit.flush, and it will just do that a few times. A little tiny test program should get a few traces and a few flushes. And let's run with the audit log. I'll expect this in, oops, give it a variable name. Oops, amazing. This actually I don't get. Do we overwrite the file? Did it get overwritten by the audit log or something? No. Not sure why flush to lure is getting overwritten. Doesn't make any sense to me. Is there something special about the name flush to lure? Test f.lure. Why is that getting written over by binary? That's not what we want. One step at a time. Set that back. It should be. And we want to then decode our order log. Pardon me, we're going to come back to that. I'll write it down. I have a bug when we introduce the command line parsing for the audit log or something. Might lose that. So message pack input will be auditor log. We go in debug mode and continuous mode. So do we get any flush events there? No. Why didn't we get any flushes? File is auditor log. Timestamp is correct. Yes. Look for the events. New prototype, blah blah blah. That's definition of bytecode. Mixing, there's loading source code. Trace stop, trace stop, trace stop. Okay, interesting. So we're not getting the message logged. Did we do a make? No, that could explain it. Let's try that again then. And when I did the next build to build and do the test suite, that ran in a sandbox, so it didn't actually update the working copy. So I think I actually just ran the old code. We try that again. Now what do we get? Now we get a flush all event, referencing a JIT state at that address. And we had logged a JIT state at that address, which is good. We should have some earlier instances of that. Flush all. Yes, okay. That looks good. Getting our log populated. We will commit that. Very good. And then we will be able to use this logging actually to sanity check that, see whether we got the behavior that we expected, and then go on to, after flush, we're going to want to increment a bit of JIT state somewhere saying what the current generation of code is, and then we're going to want to make the profiler support multiple generations and be clear about which generation the profiler samples refer to. But now it's lunchtime, so that was kind of a reasonably satisfying little morning live coding session. Thanks for playing along, and more RaptorJIT profiling glory the next time around.